Now finally, we will prove rule number 6 of the differentiation formulas. Specifically, we'll prove the quotient rule. The derivative of f over g is equal to g times the derivative of f minus f times the derivative of g over g squared. In other words, if I could call f the top function and g the bottom function, I would state this as the derivative of the top function over the bottom function is equal to the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. Alrighty, here we go. Remember, we're going to use the limit definition to prove that this is true. Continue. Okay, the derivative with respect to x of f over g of x is equal to the limit as h approaches 0. Now let me pause this before we get started. You know what we're going to do here. We're going to use f over g in the limit definition instead of just f. Here we go. F of x plus h over g of x plus h minus f of x over g of x, and all of this over h. Okay, next we're going to go ahead and do something kind of tricky. We're going to repeat everything you see above the limit of f of x plus h over g of x plus h minus f of x over g of x all over h, then multiply by a strange form of 1. G of x plus h times g of x over itself. That's 1. Anything over itself is 1. So that's a legitimate move. So I'll just make a note. We just multiplied by 1 here. All right, now let's mix it in. We're going to distribute this multiplication across the top and leave it on the bottom too. Gives us a limit of f of x plus h times g of x minus f of x times g of x plus h all over h times g of x plus h times g of x. Now you might have to pause this and think about it to make sure that this is true, but it is. That's equal to the limit of f of x plus h times g of x minus g of x times f of x plus g of x times f of x times f of x minus f of x times g of x plus h all over that crazy denominator h times g of x plus h times g of x. Okay, now we're going to clean up. And actually what we're doing is we're factoring out the g of x upstairs and the negative f of x upstairs. Gives us a limit of g of x times bracket f of x plus h minus f of x. Close your bracket, minus f of x times bracket g of x plus h minus g of x, close bracket, all over that crazy denominator h g of x plus h times g of x. Now another trick, we're going to multiply by another strange form of 1 over h over itself. We're trying to set this thing up and we have not done anything illegitimate yet. So here we just factored out the g of x and the negative f of x, and we also multiplied by that strange form of 1 over h over itself. Now let's distribute the 1 over h and the limit. That'll give us g of x times the limit of f of x plus h minus f of x over h. See, we went right over g of x because g of x does not depend on h, so we can just pull it right outside of the limit. Minus f of x times the limit of g of x plus h minus g of x over h. Again, we were able to pull f of x outside of the limit because it doesn't depend on h. And on the bottom, we have g of x times the limit of g of x plus h. Only the second function depends on h, so we were pulling the first function out in front because it's independent of h. So that's what we did there. We just distributed 1 over h multiplication, and we distributed the application of the limit. Now, finally, we're going to let h go to 0 in all of these limits on the top and the bottom. Let h go to 0. We get g of x times the definition of the limit, that's d dx of f of x, the definition of derivative, minus f of x times the definition of the derivative, d dx of g of x, all over g of x times g of x when you let h go to 0, which is g of x squared. That's just using the definition of the derivative. And there it is, exactly what we wanted to prove. We are finished.